Good evening, and welcome to the PARC Forum. My name is Bob Price, and I'm a research scientist here with the Interaction and Analytics Lab. Like many of you here, we're interested in the problems of modeling and reasoning about complex relationships between people and entities to create applications for our clients. And so we're very excited to have one of the pioneers in the field of statistical relational learning here tonight, Lise Getoor from the University of California, Santa Cruz. So Professor Getoor started her career here in California, doing her undergraduate at the University of California, Santa Barbara, and her master's here at the UC Berkeley. She worked for a time at a startup in Silicon Valley and also worked at NASA Ames. And then she returned to do her PhD with Daphne Koller at Stanford, where she helped to create one of the first probabilistic relational models, the PRM, in the late 1990s. And based on this work, she was able to secure a professorship at the Department of Computer Science in the University of Maryland, College Park. Since that time, she's published widely in many fields related to machine learning and reasoning under uncertainty. And applications include link prediction, collective classification, entity resolution, data management, data integration, visual analytics, and social network analysis. For the depth and breadth of her work, she's been recognized with many awards, including 8 Best Paper or Best Student Paper awards, the National Science Foundation Career Award, and a Fellow of the Association of Artificial Intelligence. Professor Getoor is also an active contributor to the machine learning community. She has served on the program committee or co-chaired, I think, every major conference in our field. And she is a board member of the International Machine Learning Society. Recently, she returned to California to take up a professorship at the University of California at Santa Cruz, where she is currently leading the Data Science Initiative. And here she is contributing to our understanding of key issues in machine learning and analytics for structured data, as well as assisting local companies in efforts to transform their data into the new applications that are making all of our lives better these days. I recently learned that Professor Getoor is also an alumna of PARC, having done a summer internship at PARC in the late 1990s. And so I would like to say welcome back, and I hope we see more of you now that you're in the Valley. And we look forward to your talk tonight, Professor Getoor.
Yeah, so it's very nice to be back. It's nice to be back at PARC. It's still as lovely as when I was here before. I'm getting used to the drive over the hill, so I made it pretty quick. Let me start with the most important part of the talk, which is acknowledgements. One of the things that's so great about being a professor is all the awesome students you get to work with, and I've been very, very fortunate in the students that I've worked with. Right now I have my LINKS, which stands for Lisa's Inquisitive Students East, so I still have a bunch of students at Maryland. I'm building up my group here at Santa Cruz, and all of this is thanks to them, and it's also thanks to sponsors that make this research possible. So before I get into the bulk of the talk, let me give a little bit of context. There already was a fair amount of context in the introduction, but my research areas kind of span 3 of the really important areas within data science. They span machine learning, databases, and I dabble a little bit in InfoViz, so I've done a few visual analytic tools. But my work is also very motivated by applications areas. So application areas like computational social science, computational biology, computational sustainability. And one of the things, as you start working in all of these diverse domains, is you realize that if you look at the data is not flat. And in particular, when you look at big data is not flat. Big data is multimodal, multi-relational, spatiotemporal, multimedia, and the entities and the relationships are very important. So how many of you would say you work with data? And keep your hands up. And so how many of you would say you work with graph data? Okay, so I had a few people lower their hands, and I'm really hoping that by the end of this talk, everybody will start seeing the graphs everywhere and seeing that even some of that data that seems very flat, there may be an opportunity to exploit the relational structure and links between things. And so what I really believe is that we need data science for graphs. So this needs to be a new field. And so, of course, we have the V's. So we have the 3 V's, the 5 V's, the 7 V's, however you count. So we really need a new V. And so I've been looking for a V that actually gets to this graphy nature. And so does anybody have any good V's? Because I'm going to show you the crummy one I came up with. So if you guys have a better one, I'm going to replace it. Okay, well, if you think of one later, especially after you see mine. Vinculate. So I was visiting Penn State. They have this big social science data IGERT program. And one of the political science professors said, you know, I have that Latin word for you, vinculate, which means to tie or to bind. So I think we should add this to our repertoire. So in this talk, what I'm going to go through is kind of 3 different components. And one is just kind of graph analytic patterns. And these graph analytic patterns are just kind of the pieces that I think go into many graph algorithms and that we need to have support for them. Then I'm going to talk about some techniques, and these techniques are things that are applicable across these patterns. And then I'm going to get a little bit into tools. And I'm hoping, because I know this is kind of a diverse audience, that the first 2 should be kind of pretty accessible. They're abstract, and I think are kind of key ideas that are useful when you're talking about a need for science, for a data science for graphs. And then the tools one, I'll get into a little bit more technical detail. So the first one is patterns. And the common data analysis, graph data analysis patterns I want to very, very quickly introduce are the following 3. And let me start with the first one, collective classification. So again, you know, have a graph in your mind. Collective classification is inferring labels for the nodes in the graph. And so let me give you a toy example to motivate this and ground it a little bit. So you have a social network, and the social network you're trying to figure out, are the individuals in the social network either Democrat or Republican, left or right, some sort of political party. And you have relationships, and these relationships can be friendship links, they can be familial links, they can be coworker links. You can think of all kinds of different ways things can be connected. And the problem is, I may actually be in the lucky state that I do have labels for some of the nodes, but I have a bunch of nodes that are unlabeled. And in this case, I'm doing it half and half. So I'm saying half are labeled and half are unknown. Usually the real case is that you have, like, you know, some very, very small percentage that are labeled, and then a huge number that are not labeled and that you need to infer the labels for. And so this is the problem of just doing inferring, simple problem, inferring labels for nodes and graphs. The next pattern I want to talk about is link prediction. And link prediction, again, is a very simple concept. So I'm trying to predict edges in graphs. And let me start with, give a little example. So here, maybe I have a communication network. So I have people, and they're sending emails to each other, text messages, so on. And we have some observed relationships, so the communication links, co-location, things like that. But we want to predict other kinds of links. And these other kinds of links can be some form of semantic link. It could be figuring out the organizational hierarchy, who works for who, who's friends with who. And you can realize that this is the same thing that would be behind some sort of recommender system. I'm recommending, who you should become friends with and so on. So again, just a pattern, a little pattern, which is predicting links. The third one I want to mention is entity resolution. And entity resolution is the problem of determining when two nodes in some observational graph actually refer to the same underlying individual, or the set of nodes that refer to the same individual. And one of the things that's actually very entertaining about entity resolution is it goes by a lot of different names in a lot of different fields. So these are just some of the different names that basically mean how do you figure out when things are co-referent. And I'm always collecting more of these, so if you guys have a favorite term that's not up here, feel free to let me know afterwards. But entity resolution is a problem that I think is hugely important in graph data analysis. And let me try and illustrate that with just this tiny fragment of a real data set. So this is a co-author network. The nodes are authors and the links are co-authorship links. And it's interesting, this was used for an InfoVis challenge in like 2004, and supposedly the data had been extensively hand cleaned. The experts were looking at the data, there was no bugs in the data. But if you look at it even just for a little bit, you start noticing some kind of peculiarities about that little portion of the database. And so this is what you get after doing the entity resolution. This is what you had before. And so you think of any graph analytics that you compute on this first graph, whether it's as simple as degree distribution, count of nodes, connectivity, is going to be completely wrong. And so you're going to get incorrect answers if you do your work on a data set that hasn't been properly resolved. And also in this setting in particular, this kind of looks, if you're just looking at the data even, it looks kind of like a spaghetti mess. But this one tells a nice story. There's a clean co-author clique going on. And so it's important to do this kind of analysis before doing anything more. And I'm going to talk a little bit more about entity resolution, but if it's a topic that you're interested in, we have a lot more information in a tutorial that I've given with Ashwin Machinavajala. The slides are available from my website. Okay, so these are just the 3 simple patterns that I want to bring up. Next, I want to talk about some techniques. And these techniques, I'm trying to frame them in a general way so that they're going to be useful to people no matter what kinds of methods they're using. And they will work for all of these patterns. They have applications for all of the different little subtasks that I just talked about. And these are the 3 techniques that I'm going to go through. And the first one is relational classifiers. And so, again, this is getting to the how do I go from flat data to graph data. So traditional machine learning approaches, statistical machine learning approaches, assume that I'm given this nice random sample of homogeneous, identically distributed instances. And then it's fabulous. There's all this kind of beautiful theory for saying, you know, when I can learn something, what the convergence rate is, generalization, you know, all of these things. But how do we deal with graph data where this doesn't hold? So here's my cartoon illustration of IID classification. So we'll start from there and see how we get to relational classification. So here the idea is that there's some y variables that I'm trying to predict, and I have some features, and these are the x's. And I'm going to be given a training set where I get to observe the y's and I get to observe the x's, and I'm going to somehow output a classifier that will predict y given these. So I have these nice flat instances coming in, and then I can apply my favorite classifier, you know, whatever the most popular is, or whatever you have the code for, whatever runs fast. And so we're set. So now how do I go from this to dealing with graphs? So first off, the difference is, one of the differences is now I'm going to have links between things. And I'm going to make this figure a little bit easier to interpret, I'm going to kind of collapse the x's into the y's, and so these are my instances. And now, in addition, because I'm in this rich graph setting, I could have some kind of links to other kinds of entities or objects, these kind of orange squares. I could have different relationships to other kinds of objects, these purple octagons. And then the question is, how do I make predictions here? And the first thing that I'm going to look at is label prediction, where I'm trying to predict the labels on these nodes. And so I want to predict y given all this information. And what I can do is, again, I'm going to form these vectors where these vectors will still have the x values, but they will also have, and so the x values, I'm going to call these the local features. But in addition, I'm going to construct additional features that describe the kind of graph neighborhood that these are in. So these I'm going to call relational features, and they can be things like counting the number of labels, number of neighbors of a particular kind of link, the average value across some neighbor, and a variety of different things. I mean, this is really kind of where the creativity comes in terms of all the different kind of features you can compute here. And once I have these, then I can again, construct a classifier from this. So this is one, label prediction, predicting the label for a node. The other task would be link prediction, so predicting a relationship, and this could be a co-referent relationship, or it could be some sort of semantic link. And again, I'm going to do something where I construct vectors, but now I'm going to construct them for node pairs. So for each possible link between the different nodes, I'm going to construct a feature vector. And typically this feature vector, again, we have our local features, but then oftentimes you have some sort of match features that says, is this value the same for these two nodes? Or how similar is it between these nodes? But again, you can construct other kinds of relational features that are based on the number of shared neighbors and so on. And participating in a relationship, you can think of all kinds of things. And so this relational classifier that I've described we're going to pre-compute the features over the observed information. Then we're going to represent this as a fixed length attribute vector, feature vector. The instances are treated independently of each other, and then I can apply any model. And so the key idea behind this, and the most important thing here, is the actual feature construction. This is where the art comes in. How do I construct features that summarize the graph context for a node? And how do I come up with features that capture the aspects of potential node pairs? And so normally when I give a tutorial on this, I would go into like 20 slides that list all the different possibilities here. If anybody's really interested in this, send me an email. I'll point you to some slides that go into details here. But this is one of the kind of most important aspects here, is the creativity in constructing these features and constructing features that are actually computationally tractable for computing. So the pros of doing this are it's flexible, efficient. We can use well understood methods. Not surprisingly, there's some cons. The biggest one is this is making really incorrect independence assumptions. And so, it's hard to impose larger constraints on the structure as well. And so while I do advise people, if they're doing some sort of graph analytic problem, that you should use this as kind of your baseline. So start off, do a relational classifier, see how good you can get. Oftentimes they work surprisingly well, even though they're wrong. But it's the first thing that you should do. The next thing that you should do is think about doing collective reasoning. And in collective reasoning, what I mean is kind of using the graph structure to propagate information. And an example of that in our node labeling example from before, where I'm trying to predict a label, a political persuasion for an individual. Well, again, I'll start off with the information that's just local information about, who they contribute to. So if they donate to a particular party, that's signal for what party they belong to. Information about, what they tweet and status updates, so I can look at kind of words that occur there and so on. So I can use all this kind of local information to get an initial, perhaps, guess for the label for a node. But I also want to use the graph structure. And so I want to use things like the notion that, well, if their friend votes for a particular party, then they're more likely to vote for a particular party. And if their spouse votes for a party, then maybe they're even more likely to vote for that party. And so this kind of relational information is something that's important to exploit in coming up with the best labeling for all of the unknowns, and doing it in a way that depends on each other, so that I might start off as, I infer that this node is a Democrat. Then going from there, I infer a label for this node. And then finally, I infer a label for this node. And there's a variety of different algorithms that can exploit the graph structure in a way that you do this so that it's not independent decisions the way that it was in the relational classifier. An example of this kind of collective reasoning that's useful in the link prediction task is I can do things that, say, figure out the kinds of emails there are. So there might be deadline emails and social emails. Then I can say, if someone sends a certain kind of email to someone, if they send deadline emails, they're more likely to be a supervisor. And then I can include things like definitions saying, well, if A is the supervisor of B and A is the supervisor of C, then they're colleagues. So I want to do this kind of collective reasoning about the relationships between individuals. And then also in the entity resolution case, I also want to do something similar where suppose I have these two nodes, I'm trying to figure out if they're the same. I can look at information about the name strings or the name field and use some sort of string similarity measure to figure out if they're referring to the same thing. I can also use information about the neighborhoods. So I can say, okay, if there's overlap in the neighborhoods in terms of the friends, then they're more likely to be the same. And note that there's going to be this propagation effect happening. As I figure out that these two are the same, then that's going to give me more information that makes it seem like these ones are the same, and so on. And then finally, I can encode certain things like transitivity constraints. If A is the same as B and B is the same as C, then A and C are the same. But actually, one thing that we have found in most of our applications of entity resolution is enforcing this as a hard constraint is too strong. So you'll get actually better quality results if you make this constraint that's highly likely not to be violated, but not actually a hard constraint. So the key idea in what I just talked about for collective reasoning is something where I'm going to be able to capture patterns of dependence, and they're going to be repeated multiple places throughout the graph. I'm going to have a way of describing this commonality, and I'm going to have a way of doing inference in these models. Oftentimes, the underlying semantics for these are something that's called a lifted graphical model. I'll talk about one particular one of these a little bit later in the talk, but if you're interested in this area, there's been a bunch of approaches proposed recently. This whole area of probabilistic programming is very closely related. And this is a survey article that goes through a number of different approaches. But the key idea is that you kind of have this way of templating the dependencies. The dependencies repeat in multiple places, and then you're doing collective reasoning where you're jointly inferring the labels for the unknown variables, not doing it independently. Okay, so in terms of analysis techniques, relational classifiers, collective reasoning, and then I want to talk about a third kind of general technique that is applicable to all the problems and is very important to consider, especially when you're doing link prediction or entity resolution, which is blocking. So one thing, hopefully some of you noticed when I was talking about the link prediction task, is that I suddenly went from n variables, which was the number of nodes, to n cross n, so n squared. Now, yeah, it's fine to do that for 10 nodes, but even for 1,000 nodes, and then if you get to big graphs, there's no way that you can do this. And so as one simple example, suppose I have 1,000 business listings from 1,000 different cities. If I tried to do all of those comparisons, and I'm doing it 1 microsecond, that's totally unrealistic. It would take much longer than that to apply some classifier. It would take 11 days to do this. But if I took into account, the different cities that places are in, and then say, well, I'm only going to match within the same city. So things from different cities, I'm going to just assume they're different. I'm not going to bother inferring whether or not they match. Then that reduces the number of comparisons from 1 trillion to 1 billion, and I can do this in 16 minutes. So this general concept of kind of not computing all of the potential relationships is really important. And there's two, the idea is that you have the set of all possible links, you have the set of true links, and then I want to somehow avoid doing all of this light blue square by figuring out some blocking criteria and say, I'm only going to compare the things within here. I'm going to miss some stuff, so the blue stuff I'm going to get wrong, but I will save a ton of work, and I have to kind of analyze that trade-off. And so the technique for doing this is to use blocking algorithms. The simplest approach is use some form of hashing algorithm, so something that you can compute quickly. One can do things like just a deterministic function of attributes. So people will do things like the same first 3 letters of a last name, or people that are in the same city and state and zip, or things like that. That works okay, but sometimes you get very different sized blocks. So think about Smith, the SMI block would be huge. So people have developed methods for learning these. And then one of the very kind of elegant approaches is to use some form of locality sensitive hashing for doing this. And there's been a number of approaches that have been developed for specific distance metrics to do this efficiently. So hashing is one approach. We can also do something based on clustering, and this allows you to have kind of overlapping blocks, and that can have some advantages. There's techniques based on sorted neighborhoods, canopy clustering, and this is a very active area of research, how to do this in a good way. So these are the kind of common techniques that I think are useful for any kind of algorithm trying to do any of the patterns that I've talked about so far. So now let me talk about some of the tools for doing this. And these tools are actually motivated by the fact that, I talked about these patterns. I talked about doing the collective classification, the link prediction, and the entity resolution. Really what we want to do is we want to do all of them at the same time. So we have this big observational graph, and from this observational graph we want to kind of infer the right graph, and inferring that means filling in all the missing values, predicting all the links, getting the entity resolutions all done properly. And we need scalable and declarative tools for doing this. So we've developed a number of tools in my group. As Bob mentioned, way back, PRMs were looking at things like this. But one of our most recent is this couple of collective classifiers, where basically we take a collection of unnormalized conditional classifiers and propagate the information. I'm not going to talk about that here. Instead, I'm going to talk about our newest tool for doing this, which very much builds on work that we learned from doing this, and then wanting to impose more complex constraints and building on other probabilistic programming tools that have been developed in the community. So these are some of the folks involved. Steve Bach is kind of the lead developer right now. Bert Wong is also very actively involved. Matthias Broekler, who some of you may know from Titan, the graph database, is also one of the people who is very involved in the initial development of PSL, and a collection of other students. So PSL is a declarative language based on logic for expressing these kind of collective reasoning problems that I've been talking about. And we're going to have predicates that can represent relationships or properties. One of the things that's different, and that's why it's in red here, is the random variables in this model are going to be continuous valued rather than 0, 1 like some of the existing approaches. I'm going to talk about the advantages of that in a sec. We're going to have rules that capture dependencies or constraints. And one of the things that we found in these kind of graphy domains is that we very often had to reason about aggregates. So we had to reason about the similarity between neighbors and sets and so on. So we found it useful to have that as a primitive that was actually supported in the language. And then a PSL program basically is some sort of an input database together with some rules, and that will define a probability distribution over all of the unknown variables. And I'm going to tell you a little bit about how we compute that efficiently. So let's go back to our example from before. So the rules actually do look something like this, where we can talk about links and dependencies. And what this translates into, because I'm going to translate it into a certain form of a Markov random field, is I'm going to make the reasoning scalable by mapping these logical rules into convex functions. And we don't want to think of these as rules that hold all of the time. So we're capturing that notion. And these weights indicate how probable each of the rules is. So the general form for the rules are, you know, we have this conjunction and disjunction and weight. Now, I'm going to translate that into a weighted logical clause. So I'm going to translate the rule into a disjunction where I have some positive literals and some negated literals. And again, something that's different from this, about this than for Boolean logic, is the variables take values in the range between 0 and 1. And so each of these clauses is going to define this linear function where I'm going to sum up all the positive literals. For the negative literals, I'm going to take their value and subtract it from 1. And then I want to check how far this sum is from 1. And this captures how far the rule is from being satisfied. So if you think about it a minute and you think about it in terms of standard Boolean logic, this translates. But now we've allowed these variables to take on a value between 0 and 1, and we're also able to talk about how satisfied a rule is. Now, given this, we can actually justify this interpretation under 3 quite different rationalizations. And I'm not going to go into the details here. Actually, this is very much kind of fresh off the presses. When we started off doing these, we started off thinking about and coming up with these because we wanted to have these continuous values. But it turns out that one of the really nice things is that we can actually get guarantees for this max-sat interpretation of PSL. So this is giving us our kind of interpretation. Now, what is the mathematical object we've just defined? We've defined something called a hinge loss Markov random field, where we have the probability of our unobserved variables given our observed variables. This is kind of a standard format, but the key thing is what's going in the exponent here is the sum over all of the rules in our program, the distance to satisfaction, and then raised to some power. Now, the really cool thing about this, and the thing that's very distinct from the case where you have Boolean variables, is this ends up being a log concave function. In order to optimize it, this is very nice. It ends up being optimization that we can solve directly using some off-the-shelf convex optimization problem. So this makes inference. So inference is figuring out the probability of those y variables extremely tractable. We can speed this up even more by using state-of-the-art optimization techniques like ADMM and architectures like GraphLab, some sort of vertex programming. We've implemented this. One of the things that's very cool about this formulation is you get this very fine-grained parallelism in terms of each of these little hinge loss functions. You can kind of optimize them independently and then propagate the information using something like ADMM. We found that it outperforms discrete MRFs in terms of speed, and by outperforms I mean orders of magnitude outperforms, and oftentimes we get higher quality answers. I haven't talked about weight learning, so I showed these weights. You don't have to specify them yourself. You can learn them from data. We're using kind of standard techniques for learning the weights from observational data. And then one of the things we're very excited about is we're also currently developing latent variable models for these, where you're able to model hidden variables, and again, it's not as efficient as this case, but still highly efficient methods for doing inference when you have latent variables. And one of the things that we really like about PSL is its flexibility. So we actually have applied it to a number of different domains, including some basic computer vision settings where you're doing low-level image reconstruction or higher-level activity recognition. We've applied this to some computational biology settings, drug target prediction, and so on. One of the areas that I'm particularly very interested in is computational social science. So how do we use this for modeling social media, social relationships? How do we learn about latent variables? One of the domains that we've been looking at this in like political discourse, sentiment analysis, psychological modeling, but we're also doing it in modeling engagement in MOOCs, and trying to look at student engagement, trying to predict who's going to complete the course, what kinds of engagement do they have, and so on. Something that I do a lot of, you can kind of tell from the entity resolution stuff, is the data integration. So these kinds of techniques can be used for discovering mappings between data sources, and that's another area that we work on actively. So, what does a PSL program look like? Well, for those three toy examples that I gave, this is what a PSL program looks like for that collective classification problem where I'm trying to figure out the labels for nodes, or the political parties for nodes. Notice that you can add in arbitrary linear constraints. This one is saying really you're kind of either a Republican or a Democrat, so you can't be all of them at once. Oops, that does not look good. I don't know what happened there. Anyways, somewhere in there, there's a program for the link prediction. And then here's a program for the entity resolution. And you know, you see you can define the blocking predicates here, make use of them. Here we're doing this kind of set similarity. We're doing an approximation to the Jacquard in this case, and then we have kind of domain and range constraints that can be encoded. But you know, each of these is, you know, a small program, and you can think then about kind of combining them all together. So if you want more information about that tool, it's open source, it's available here. There's videos that go into much more detail about how it works. In terms of kind of wrapping up, I want to go to these kind of back up to the patterns, techniques, and tools. And I really feel like we're just at the start of understanding what data science for graphs should look like. There's a lot of excellent work on graph databases, scalable storage for graphs, and so on. There are interesting platforms now getting to the analytics, and what are the analytic patterns? So the ones that I just put up, these patterns of node and link and entity resolution, these are just the baby basic patterns. We want something bigger. I think that as we do this more, we will discover these kind of common patterns, just like collaborative filtering is now something that everybody's aware of, these kind of personalization in graph settings and also community optimization in graph settings. And then I have not said anything about taking actions or making interventions and so on. So all of these, I think, are upcoming areas and needed. So we really need new statistical and ML theory for large graphs. I think the being able to handle methods that understand bias, you know, we're dealing with all this data that no longer has been collected in an independent manner. It's observational data. It has all kinds of bias that one could make use of. Understanding causality, of course, is hugely important. And all of the other kinds of traditional issues in statistics, how do we kind of build new theory when we're in this kind of new world of very heterogeneous, rich data? Some important topics that I didn't manage to touch on. I hope a few of you felt a little bit iffy, ouchy about my graph identification problem, that we're going to take all this kind of observational data and then we're going to infer this network. There are very important privacy issues, and I think we need to understand the statistical power of the kinds of things we can infer when we have a network so that we can really judge our privacy, the privacy implications appropriately. Also visualization, you know, I mentioned this at the very beginning. I didn't manage to talk about it in this talk, but I think when you have these kinds of complex statistical inferences that you're making, if you don't pair it with a graph viz that allows you to kind of understand the implications of what you're doing, understand what's happening, I think that that's just not responsible. So I think we need to have methods that kind of marry the InfoViz together with the data analytics. I'm very interested in methods that do model comparison. So, you know, I have a bunch of different possible models. I want to understand where do they predict the same thing, where are they different, then how do I drill down and how do I understand things based on that. And I think there's tons of interesting opportunity here. I think there's opportunities to develop new research and apply them to really compelling business, social, and societal problems. So, thanks.
Thank you very much. We have time for a few questions for the speaker. Yes?
So in the PSL, you said you had to map the variable into a convex function. Is that right? But what's the significance of it being convex?
So the key thing is the difference between when I then combine them all together and then get a convex function. Optimizing a convex function versus a non-convex function are orders of magnitude different in terms of complexity. So I really like it when I stay in convex land. And that was a lot of the work, kind of figuring out that this still would end up being convex, and then we could have the benefit. Of course, then when you throw in the latent variables, you lose that, but yeah.
Yes?
Here.
So if I were to explain why the data science of graph is different,
Yeah.
is it that fundamentally the links are extra features, or there are special features that we have to somehow treat them differently?
It's exactly that, and it's exactly that one way one can treat those links is just as extra features. And that's kind of what the relational classifier was doing. It was just doing, smart feature construction using that. But it was assuming that then the nodes were independent. Another way to use a graph structure is actually to use it for propagating information and really reasoning about there's some dependency between these. And so usually you want to do a mix of those. Depending on your mathematical framework, there's different ways of kind of looking at that and rationalizing that. They're closely connected, actually. But just in terms of when you're going from not being used to thinking about graphs to thinking about graphs, thinking first about the feature construction and then about the collective reasoning, and checking whether your domain is really a domain that can benefit from this collective reasoning, or is the relational classification, enough? Yes.
Kind of continuing the same theme of what's happening in the mathematics, Lukasiewicz logic. Do you have any special thing to say about that, apart from what you said about the implication case being kind of close to one and stuff like that? Do you have any, it's one of the fuzzy logics, but kind of what else?
Yeah, so that's a good question. So our initial approach was motivated by that interpretation, but we wanted this fuzzy predicate partly because the first problem that we were looking at, we were doing ontology mapping. And we found that kind of this 0-1 kind of notion just wasn't the right notion for that. Now we've looked at other norms, and the big question is, when do they maintain the convexity versus when do they not? And so I think there are other norms that it will work for, but then I know that there's some that unfortunately it won't work for. But we're kind of just, so I should have probably caveated, PSL is very fresh. So it's a new thing. We're extremely excited about it, but there's much research and other things to do with it. Yeah.
The graphs you showed are all static. You did mention something about activity recognition. Does anything fundamental happen when the graphs change through time?
So definitely dealing with dynamic graphs is incredibly important. And yes, I here was focusing on static graphs, and most of the stuff that I personally have done when it's been dynamic, it's been pretty trivial, where we're not modeling the process, the evolution process, in any deep way. I think that mix, like as one gets to kind of efficiency manners of dealing with dynamic graphs, certain kinds of things like streaming and so on are important. That actually is something that we're looking at in the context of knowledge graph identification, which is something that we do. But to fundamentally get to modeling dynamics is also something incredibly interesting. And as we get into these kind of causal models, figuring out where that fits in the process, and then how do you do inference efficiently. So can these kind of dynamic models, what's the lifted version of a dynamic model that you're able to then solve efficiently? So I'm kind of touching a bunch of different places in the dynamic graph space. I'm sure I've left out some, but yeah.
A quick question on, sorry, losing the train of thought here for a second. Transitive relationships that are often handcrafted, such as triadic closure rules.
Right.
Are you able to, if you constrain your machine learning techniques enough to stay within a single link type, do you find that you are able to discover what were previously handcrafted models, but just as an output of machine learning?
So we definitely, actually, so one of the domains that we've looked at is social trust. So figuring out who trusts who. And in that setting, there's a couple social science theories. So one is a structural balance that people are probably familiar with. You know, I trust my friends, who they trust, and so on. And if they're enemies, then you know, the enemy of my enemy is my friend, and you know, all these things. So there's different kind of valences of the triads that you could look at. Another theory is more of a hierarchical theory that says, you know, I trust the people above me in the hierarchy, and I don't trust the people below me. And so we've been able to encode like 2 different models that capture different patterns, and then figure out which of the 2 was a better fit for the data. And that was all based on kind of looking at the these kind of triadic rules and discovering which ones held.
On the question about dynamic graphs, can you look at problems of trying to optimize graph relationships?
Optimizing graph?
Optimizing the relationships between nodes in the graph. So you're trying to, you have a static graph, you know the relationships, the graph is actually moving, and the relationships between the nodes are moving. Well, the properties are changing.
Yeah, so the way that we framed it here is the kind of link prediction task where you have some observed links, maybe those are different kinds of links, and then I'm trying to infer the relational structure. And so I can infer the graph from this information. The level at which we've done it dynamically is, you know, pretty crude, just kind of time slicey kind of things. So I think one can definitely do smarter things there. But there is this notion of I will collectively infer a graph given some observed graph and other kinds of information.
I'm not sure how you add probability to PSL. I understand how you make the variables non-linear. I didn't quite understand how you got rules that have probabilities.
So one thing, if I set it exactly as the rules have probabilities associated with them, I misspoke. So the rules have weights with them, and the weights will tell me kind of the relative importance. Say again?
Are they generated from the data?
They can be generated from the data. And then the probabilities come in terms of defining this huge Markov random field where I am able to say something about the probability of an assignment to all of the random variables in the model. And that's composed of all of these different potential functions that are coming from each of the rules and how far from being satisfied they are, but they all kind of interact together.
So, following up on the learning part, is there much scope for actually learning these rules from the data?
Yes, definitely. So as I said, we can learn the weights, we're doing learning of latent variables, so that is kind of a form of structure learning. And then if anybody's familiar with my work, I've done a lot of structure learning, and so I'm very eager to get to kind of learning and the rule structure. Right now we're doing it in a kind of constrained setting where we're doing it for schema mapping. We're discovering the mapping rules, and I think that that will end up generalizing. So.
One last one.
Okay. That was about related to label prediction, predicting the label of the nodes. How would be predicting the label of the links? This person is a friend of that person, this is a spouse of that. How do you approach this problem?
So again, you can do that in a similar way to the way that I described. In some ways, you can think of the existence is a 0-1 variable that I'm predicting, but then I can add in, I'm going to predict a label for that. And the big thing to deal with is, you know, the explosion of the number of potential edge labels that you need to reason about. It also is one of these things that, you know, with graphs, it depends how you squint at it, whether it's a node or a edge, you project it in all different ways. And so, yeah, it depends if you want to think of it as a label or think of it as a new link, so on.
Very good. Thank you.